Okay, seems we're on. Welcome to my talk about plain functional programming. This talk was originally labeled as a beginner's talk, and I think it will start off easy for everyone to understand, but it will end off with some new things that should also be interesting for the experts here. So, plain functional programming. Let me start off with a question. What do you think is the biggest difficulty in software engineering? What are we all fighting with?
Usability.
Naming variables, usability. Off by one errors, yes. Only two greatest difficulties, and you named them. I would say no, it's complexity. Complexity is the mega difficulty we're all fighting against. It's after all, software systems get replaced not when they wear out. Bits don't rot, like Gilad Bracha says, and he says it's a shame they don't. But they get replaced, hopefully, when they crumble under their own weight because they have become too complex. That's the fate, the life cycle of a software system. It gets too complex, nobody wants to deal with it anymore, and finally people find the courage and energy to replace the software system with a new shiny one, which doesn't repeat, of course, any of the mistakes in the previous ones, and then the cycle repeats. So where does all that complexity come from? Why do we fall into the same trap again and again and again? Well, I think there are lots of possible culprits. One definitely is changing requirements. A software system is sort of a life thing. It's not a bridge that you build once and then it stands. It has to be adapted all the time. The other thing is, of course, changing developers. Developers change all the time. Developers who come new into a software system might not really understand its subtleties and might therefore increase the complexity. And maybe it's also just attitude sometimes that we are not really keeping in our mind to do the simplest possible things for fear of being labeled simpletons. So we need to do smart things because otherwise other programmers maybe think we are stupid. But overall, I think we don't really know what causes the complexity. We only know that software generally becomes more complex the older it gets. So it is essentially a constant fight. It's an uphill battle, but we still need to fight it. So what does that have to do with functional programming? Well, functional programming is important in that context because it removes one really important dimension of complexity. What is that dimension that it removes? Well, it removes the need to understand the history of the program in order to understand a single part, a function. Functions don't depend on the history, what happened before, and they don't influence the history, what happens after. Functions, in the mathematical sense, just take parameters and give you a result. That's all you need to know about them. There are no hidden side effects. And that's a huge relief because it means that to understand a piece of program, I know what I have to look at, and it can be fairly small. I don't really potentially have to trace back all the possible interactions that can be very, very far indeed. So I think that's the key of functional programming, why functional programming is important in this complexity debate. Okay, so I said, well, yeah, but what does this guy tell us? Doesn't Scala and Haskell have a reputation for being rather complex languages? And they aren't exactly the simplest languages, are they? And isn't Scala in particular a huge language containing everything plus the kitchen sink? So I've heard these arguments, and therefore I did a little bit of research. So I tried, well, can we maybe measure some of these things? And one measure I found several, but I just show you one, and they all correlate. It's just the grammar size in lines. So the grammar gives you all the constructs in your language, and I just took them all, and yes, sure, that formatted differently. I made sure that it wasn't glaring, the differences. So, and this could be off more or less by 20% for each of these languages. But here's roughly what you get. So interestingly enough, that was for me a big surprise. C++ is not on top. I thought it was on top. C# is on top. C# grammar is 1,500 lines. C++ grammar is a little bit less than 1,000 lines. And then you have Java 8, Swift, and Kotlin, more or less the same. And then you have Scala, which is a lot smaller. It's actually less than 400 lines. And you have Haskell, which is a little bit smaller than that. And you have Python, which is the smallest of them all. Well, that confirms our understanding that Python is a really simple language. And of course, I could say, well, Python is small also because it doesn't have to talk about types. Talking about types adds, of course, considerable footprint to the syntactic constructs of a language. So if you don't need to do that, then you save a lot of lines. So I would, if I haven't looked at other dynamically typed languages, but I would also assume that they're more to the left of this chart. So it's not the size of the language. I hope that I have now proven this myth wrong. But still, I mean, people perceive Scala to be complex. Where does that come from? Sorry? Scala, what? I didn't get that. Oh, Scala Z. Yeah, I'm going to talk not about Scala Z, but about some of that. Yeah, Scala Z. Well, maybe. So I think Scala Z could be part of that culture shock. So there's a huge culture shock for several reasons. So let's look at the shock part first. Functional programming is still foreign to many, and it's not just learning another language. If you learned, let's say, Python, then of course with Java you have to learn the static types, and if you go from Java to C#, then you learn a little bit more features, and it's all very much the same idea, the same approach to write programs with types or without types. But with functional programming, it's completely different, and you sort of learn that gradually as you get into functional programming, that it really demands a completely different way to think about programs, and I would argue if you do it right, a much simpler way to think about programs, but simple, as Vichicki says, is not familiar. So the simple way to think about programs might be rather foreign to the people who are new to functional programming. So it's not just learning a new language, and it takes time to adapt. And then there's the culture. So I think that some parts of functional programming have developed patterns and terminology that require a lot of learning to get into. And that sometimes contributes more to the complexity than it solves. And I'm going to try to essentially give you some examples of what the trade-offs are. It's not as simple to say, well, some people just want to throw super complicated abstractions at you, and they're obviously good for nothing. So that's not definitely what I want to say here. So let's look at functional language families, because of course there's more than one. So roughly speaking, we have the dynamically typed languages, which most of them all come from Lisp. So examples are Celos and Racket and Clojure. Clojure is the one which is most widely used in industry. And then there's the ML family of languages with currently used languages such as SML, OCaml, very popular in France, Haskell, all over the internet, and then, of course, Scala. Scala, sometimes people object to it being in the ML family because it doesn't look at all like ML. It looks more like Kotlin or Swift, or maybe that's the other way around. So the functional way is very simple. You just parameterize all the things. That's the only thing you have. If you need something, you make it a parameter, and if you return something, you make it a result. And that's great, because it means that there are no side effects. Everything is referentially transparent. The fact that you parameterize all the things in a statically typed language means everything passes a type checker. Every part of your contract is essentially checked by a type checker, and the type checker finds a lot of your errors. So for instance, if you write programs with functional collection libraries, then you will have this moment that you say, well, you write a program, several hundred lines, 500 lines, whatever, complicated operations, and it runs on first try. You were never as good a programmer before. So why are you as good in this new paradigm? Well, it's because the compiler actually was able to check essentially all the critical pieces for you, because you made them all blatantly obvious as parameters and results of your programs. So, and the other thing, of course, is it gives you very fine-grained control what you pass where. So all this is great. But sometimes it's actually too much of a good thing. If you take that principle to its end, then I think most programs end up with a sea of parameters because, unfortunately, this piece that you're looking at has dependencies on 20 other things. So, well, yes, that would mean 20 other parameters. Most of those parameters, furthermore, hardly ever change. So it's very, very boring and repetitive to pass them everywhere. And it's also prone to mistake because, you might overlook one. In a statically typed system, the compiler will probably find out, but, well, there are always exceptions where essentially it would pass the type checker. So one strategy to cope with this thing, to say, well, the direct approach is just too many parameters, too many details to mention, is to raise your abstractions. And that means typically that you take inspiration from category theory and monads. Everybody here knows monads, so that was a construct that came from category theory. And by now, I think there are many, many more. So there's a trend really towards category theory. I was looking at the program of this year's Lambda World, which was just running 2 weeks ago. And I think the conference is about twice as large as last year, so very popular. And category theory has all but taken over the conference. So it's very, very popular. So let me just show one example of what a program style that's inspired by category theory, and I made an attempt to find an example that I actually like. It's easy to just show you examples where you say everybody laughs at that and says it's clearly too complex, but I wanted to show you something to say, well, let's understand why people do that. So what the example does is it looks at the configuration problem. So it means you have a very simple code. You have code that depends on some configuration data that are in a configuration object. And some of that data might be wrong, so you have to check it and you have to react on, essentially do the appropriate thing if the data is not in the format that you expect. So there's a quite nice article called Reading Configuration with Kleiss Lee arrows, and that as an intro of that, and I'll switch directly to that article. So basically what it does is it uses a thing called Kleiss Lee, and that's a functor or rather monad, and those are two other parameters. Okay, good. So what does it try to do? So here are so here are 4 case classes. One is a name consisting of a first name and a last name. The other is an age, which just wraps an integer. Then we have a person that consists of a name and an age. And finally, we have a config object that defines a name and the age. And the task is super simple. Given the config, construct the person that is described in the config. So here's how you could do that. It's in that system. So there's a part called read name. And I'm not really sure why they wrote it as a closure value rather than a method, but whatever. So read name takes a config. And it gives you back an option of name. Option because, well, it could be wrong, and I have to return something when the thing is wrong. So then I choose to return none, which is sort of the typed version of null. So what it does, it splits the string into words using the split operator. If it finds more than one, because we need a first name and a last name, then it gives us a name consisting of the first name and the last name. Last name could consist of several words, like Simon Peyton Jones, right? Peyton Jones, 2 words for the last name. So it reassembles them with spaces. And read age is a very similar thing. It just pulls out the age of the config. It checks the age for validity. We say, well, we need to be between 1 and 150. And in that case, we return the option, a sum of this age, and otherwise we return none. Okay, and then there's the thing to say, well, now we have these options and we need to compose them somehow better. So there's this mysterious thing that we say we have this read name k, and it's a Kleiss Lee of read name. And we have a read age k, and it's a Kleiss Lee of read age. Okay, and what we then can we do with that? So the payback is here. We can write a person k. It's again a Kleiss Lee thing, which doesn't mention config parameters, and it's a Kleiss Lee of option config person. And that just essentially uses this monadic composition. It uses a for expression, reads the name, reads the age, and gives us back a person. And that somehow does two things. Somehow we put in the configuration. We don't mention it anymore here, but somehow it ends up in this Kleiss Lee thing. And furthermore, we output the option also again, except that we mention that this is the first parameter. We don't mention it anymore. So then we could say the result, for instance, here of a config with Bojack Horseman and 42 is result 1, and that would be the output of that. And here we would have an illegal configuration, and then the result would be none. So that's what we want to achieve here. Of course, you will say that for this example here, it's complete overkill, and everybody will agree with you. But people would say, well, in reality, I would have maybe configuration objects consisting of hundreds of fields and methods that access them. There could be thousands, and maybe it's worthwhile to actually hide all this plumbing in some plumbing which is higher level, which is this Kleiss Lee thing. But of course, if you're new to a code base like that, then probably your reaction would be Kleiss Lee what? Kleiss Lee what? So actually, Kleiss Lee, here's Kleiss Lee. It's actually not Kleiss Lee what, it's Kleiss Lee who. Kleiss Lee was a Swiss mathematician from 1930 to 2011 he lived. He was teaching in Freiburg, which is actually quite close to where I am, about 40 kilometers away. And he's the inventor of the Kleiss Lee category and Kleiss Lee triples. And what you saw here was an example of Kleiss Lee triples. So now I'm sure you're all enlightened. But let me maybe just redo the problem and try to come up to the problem in baby steps. So let me do that, and I'll do that with live coding. So let's look at this configuration problem again. And let's say we don't do functional programming. We just have a box standard imperative language, and we do it imperatively. So that's what we would do, I guess. So the imperative thing to do is have a global variable config. Okay, that gets initialized later on. And then we have a read name method, which does the split part. And then instead of doing this option thing, it just says require parts.length greater or equal to. Require in Scala is the same as assert, only it doesn't throw an assertion error when it's wrong. It raises an illegal argument exception. So require is sort of saying, well, something's wrong and you're to blame. You, the caller, is to blame, not me, that my code went wrong. Okay? Or in this case, the config is to blame. Okay, and then we essentially do the same thing that we do pass the first name and the last name. Read age is the same thing. It gives you the age, it takes the age, does the requirement, returns the age. And read person, so here we say, okay, in the person thing, let's say the contract would be give me a person or not, depending on whether this thing is valid. So here we do return an option, and we do that with a try catch. So I said requirement would throw an illegal argument exception. So here we catch it and return none. And if there's no exception, then we return some and the person that we got from read name and read age. Okay, cool. So problem solved. But of course you say, yes, sure, in this simple part, maybe I would even do it that way. But in a large system, I have this dependency on the config object. And let's say we do this thing, somebody changes it later on, but let's say that we're living in a reactive system. There's some outstanding computations that will come back and we have to do when essentially something triggers. But in the meantime, we have already changed the config object, and then of course all hell breaks loose because this thing would essentially start its computation with one config object, and then suddenly we change it under it and give it a new one. So we know all the insecurities with mutable state that way. Okay, let's do. So what can we do? Well, parameterize all the things, right? So let's do that. Let's just write config here 3 times. And then, of course, read name takes a config, so we have to pass the config. And we have to pass the config to read age. Okay, and we're done. So that actually, for me, is probably, and we can do this, we can delete this, and we can pass these things directly, right? So that's actually the shortest version, and probably, at least in this context, in this setting where things are still small, the simplest one. It's plain functional programming. Well, you could say no, not really, because you have an exception here, and here you catch it, and I'll get to that. So for the moment, I want to just essentially take this as an aside and say, okay, good, admit it, we have an exception, and we have to deal with that. One other objection would be the following. Let me just go back to the preview. That if we have to pass all these config parameters everywhere, and in this example it was very simple, essentially read person passed the config to read name and read age. But in an actual system, this might get out of hands. You might have literally thousands or tens of thousands parts where you have to pass some of these config things somewhere else. So you have to declare all these parameters and you have to put them in every call. That's this problem with the sea of parameters. So Scala has a very simple answer to that, a very direct answer, and that is if passing a lot of parameters gets tedious, then you can leave some of them implicit. So let's do that. So what we would write is just, we write implicit config, and here as well. And then we don't need to pass the parameters anymore. Hooray! Don't know what I did here. Okay. Oops. Yeah, there we go. So we don't need to pass the parameters anymore. And that's fine. So now we have essentially rid ourselves of the tedium to actually pass all these config parameters everywhere down the call stack into all the leaves of our program. Okay, great. So in what sense was Kleiss Lee better than this? Well, it handled exceptions with options all the way down, but let's ignore that for a moment. In what way was it better than this otherwise? Well, it didn't need those config parameters, right? That was the other thing, all these config parameters. So that's another thing where essentially the high-level abstraction, you don't need to repeat yourself over and over again with these parameters. So let's see what to do about that. So in the configuration example, we have 3 repetitions of implicit config : config. So it's an implicit parameter called config. In a large system, it can get tedious to declare all these implicit config parameters. So having to write it a couple of times doesn't look so bad. But in our new compiler, .c, which is our new Scala compiler, we actually currently have over 2,600 occurrences of the text implicit CTX context. So the context, as you might guess, is the thing that essentially gets passed into all the parts of a compiler that need to know what the current environment is, what the current context is. And that, yes, that does get tedious. And the question is, wouldn't it not be nice to get rid of them? So I'm now explaining something that will come up in the next version of Scala, Scala 3, and that is already working on the system that I'm showing you, which is essentially Dotty, which is the predecessor of Scala 3. So what I showed you in the IDE was essentially the Dotty presentation compiler that was type checking the programs in real time. So towards the solution. So how can we avoid this repetition of all these implicit parameters? Let's massage the definition of read name a little bit. You saw in the Kleiss Lee that one can alternatively write things as a method with parameters and parents here, or you can write them as essentially a thing with a lambda as a right-hand side. So this thing here is a lambda. It takes a config and essentially does then precisely the same body as you saw before. And the only difference here is it's an implicit lambda. So we can write that already in current Scala. An implicit lambda just means that the config parameter is itself available as an implicit in the lambda. Okay, cool. So what's the type of that lambda? So previously, so far in current Scala, it's a function from config to name. So that's how the function types are written. And from now on, it will be a new type called implicit config to name. So we have not only implicit parameters and implicit lambdas, but also implicit types, implicit function types. What does that buy us? Well, first, what are the rules? I mean, you can invent a new type, but how should the compiler type check programs with that? And the rules are actually, and fortunately, really, really simple. There are only two. The first rule is that an implicit function gets an implicit argument just like an implicit method. So if you have f and it's an implicit function from a to b, and you have an implicit value, which we assume is unambiguous, so there's only one that matches best, then the f expands to f applied to a. You apply the parameter implicitly. And you do that exactly the same way for implicit parameters of methods. So now you do the same thing for function types. The second rule is that implicit functions, the lambdas, get created on demand. If the expected type of an expression b is an implicit function type, implicit a to b, then b will automatically be rewritten to a lambda, which takes a parameter whose name doesn't matter, in fact, so it's not accessible to the user program, and it returns a b. So that's the only two rules that we have here. Okay, so let's go back to our thing and see how we could change that. So what I do here is I have some boilerplate code that I put to the side. Well, it's actually not, it's boilerplate removal code. It's boilerplate avoidance code. So I define a type alias configured of t, and that's an implicit config to t. So I say, well, if something gives me a t, but it needs a config to do so, then let's call that a configured t, a configured name, a configured age, and so on. And then I said these implicit function types, I can't really get at the parameter, so sometimes I need to. So the config parameter, which let me do it first, and then we will get back to that. So instead of writing implicit, so I write configured of name. Oh, to do that, I need to import. What was this called? Configs. Okay, so that's a configured name, and that's a configured age. Oops. I'm not very good at editing standing up. And that's a configured option person. Okay. And everything still works. So the absence of red twiddles means it's type checks, and I assure you it also runs and does the right thing. So, so what that means is that now I have. So let's see what I got. I avoided the implicit parameters and I put them all in the type. Why is that good? Well, let's say you have not one implicit parameter, but 5. You have to write 5 of them each time. With a type, do you have to write 5 nested types? Yes, but with a type you can alias it. You can invent an abbreviation. We do that all the time in software construction. Once something is first class, we can name it and use the name instead. And because the implicit functions are now first class types, we can name them and use the name instead. We have essentially here, instead of the implicit function types, we have used the configured. Great. So let's see how we will go on. Now we go further and said, well, let's come back to the exceptions. I still use exceptions. So what should we do here? Well, what would Scala people say? Well, one thing to do it well, just use a try type with options and things like that. And I'm going to use something very similar, but a little bit different. I use a type I made up myself just for the purposes of demonstrations. So it's called possibly instead of try. So I say, okay, if something is a possibly, now I have to import exceptions as well. And I say, okay, read name is possibly configured name. Okay, good. So read name is fine. Read age, we seem to have a problem here. It says no implicit argument of type exceptions can throw was found for parameter ct of method require. So this require method, let's have a look at it. I just imported that now from this exceptions object. Previously it was imported from predef. So it says, well, okay, I get a Boolean, and if the Boolean is wrong, throw an exception. But I need an implicit capability that I'm allowed to throw an exception. I will not, from now on, I will not just throw exceptions like this, because that's a side effect. I need to be allowed to throw exceptions. Let's call this thing can throw. So it's a class in exceptions, and it has a private constructor, so nobody can create an instance of can throw except this object itself. So where is an instance of can throw created? In the function onError, which is essentially the second part of attempt. So that's essentially try catch. Instead of try catch, which is primitive in the language, I have attempt and onError, which is now also in a library. What does onError do? Well, it says, okay, let's run this operation with a fresh can throw. I tell this operation, well, you can throw an exception, or more precisely, this only exception that we're dealing with, because I'm going to catch it anyway. So we're safe. Yeah, there won't be any escaping exceptions. So I give that capability to OP, and then I say, okay, if I get an exception, if somebody throws that exception, then I give you fallback. So I've used exceptions, which are a great invention in the JVM, because essentially they allow this non-local control flow, and they are very, very efficient. So we definitely should use exceptions. But in Scala, programmers don't really want to use exceptions. Why? Well, because they don't show up in the types. Something might throw an exception, and then you don't know what it does. So it's an undocumented side effect. So you say, well, is that something where Java actually did better? Doubtful. In Java, you have to put it in the types, but the type system in Java is super, super rigid. So for instance, you can't just define a closure and thread exceptions through and things like that. So it's essentially, you have lots and lots of problems with the type discipline. So let's see what we can do here. So I've shown you what this possibly does, and here it says, okay, no, you can't do that. So what do I have to do to fix this? I just put it in another possibly. And what do I have to do to fix this? Well, here I now say, instead of the try, which I shouldn't use because it's an exception I can't get at anyway, I do attempt.onError, and then the none. So that's what I do here. Oops. And we're done again. So what have I shown you? So we've done one thing, which was injection arguments. We can express that as an implicit function type and put an alias on it. We've seen another thing, which was effects, in this case, raising exceptions. And we've seen we can do exactly the same trick, only another name, which is possibly and configured. And we just leave the code exactly the same as it was in the imperative version. There's nothing, I haven't touched the code at all. And all I really did is I changed the result type from where we started. It was name, and now it's possibly configured name. So I would argue that's actually a great thing, because name doesn't really tell me enough. Name doesn't tell me actually this thing needs to read the config object, or you have to pass it, and it doesn't tell me, oh, and by the way, this name might be essentially non-valid, and in that case, essentially somebody has to handle the case. So it doesn't tell you any of the two things, whereas now we have it all in great detail. Cool. So you could say, good. So how does that compare to Kleiss Lee and the monads and monad transformers and things like that? So I think the answer is, once you do Kleiss Lee, where did we hear? The read person thing, that didn't look anymore like a normal straight line code. It was a for expression. And for expressions are actually rather pleasant to write in Scala. So essentially, they give you a simple surface syntax for monadic composition. But the problem is essentially you only have one freebie. So as long as you live in one monad, everything is very, very nice with 4 expressions. If you start to compose monads, it gets very, very hairy. And that's essentially where all the plumbing comes from. Whereas here, there's still no monad at all. It's straight line code. All we did was essentially pass these implicit parameters. Okay, does this thing have a name? Actually, it does. There's essentially a movement, set of very interesting ideas called algebraic effects, which is essentially a fairly new and hot thing in function programming. What I claim here is that Scala's implicits, in particular implicit function types, they are a great way to represent algebraic effects. If you see how people do it currently using monads and the other abstractions in both Scala and Haskell, then you see that they have great troubles. So typically people go to a free monad, and then with a free monad you can do algebraic effects, and by the time my head is already up in smoke. Whereas here it's as simple as essentially having these hidden implicit function types. Another thing I just can, out of spite, let's just turn these things around. Huh? Let's try this. Hey, works still. So I can have these things in any order, and there would be no type error whatsoever. So what's the other very interesting thing is these things, these effects or read effects, write effects, they behave really like sets. Order doesn't matter. You can write them in anything. The compiler will essentially find the ways to make it work. Cool. So what we have here, sorry, I was skipping 2 slides. Well, I go back to. So what we have here is really a great comparison between explicit versus implicit. Here on the left you see explicit plumbing. That's Kleiss Lee triples, monads, monad transformers, the whole thing, categorical thing. And what we have instead is completely implicit. So that means you notice the endpoints. That means the types you have and the types you want to pass. And the connections are done completely automatically. So it's really like having a bunch of Wi-Fi endpoints and not worry how something is routed. The system will take care of that. All you need to worry is that you are very specific what you have. So in the Wi-Fi point, the being explicit means I have an IP address, a unique IP address. In the implicit parameter thing, it means that you should use implicit parameters only for very specific types that you can't essentially misuse for anything else. So one of the first mistakes everybody's doing with implicit, they do an implicit that gives us a string or that converts 2 completely unrelated types because it's cool. Once you do that, you will regret it greatly later on because that ruins your addressing scheme in this Wi-Fi thing. Essentially, that will the more implicits you have, the more these overly large types will essentially conflict with everything else. So it requires a certain discipline, but once you do that, it's great. So I think in this case here, I would say normally you say explicit is better than implicit. But if you look at this and that in the real world, then I think most of us would prefer Wi-Fi connections over, let's say, a cable salad where you have lots of cables going from one to the other, or this plumbing thing here. So everything is relative here. Okay, to wrap up the comparison, let's talk about efficiency. These implicit function result types, I said they're these closures that get essentially created by the compiler. Closure creation, that's an object, so that's not free. But actually, because implicit function types are so simple, the compiler can fairly easily optimize them. And in fact, it will replace them by just curried methods, and then the cost of an implicit function is just the cost of passing a single parameter, which generally is negligible. So if we compare what we have seen now with Kleiss Lee triples, the goal of both was to essentially avoid mentioning detail over and over. One detail is, what am I reading? The other detail is, am I giving back a partial result, an option or a try or something like that? And they have the same advantages that the reading and the returning is abstracted in a type, and I can make my types very short, and a type can express a lot of things because I have aliases for them. So I have essentially lifted this whole thing to a different level. But in the examples of Kleiss Lee and monads, I would say it's much, much harder to get the plumbing correct. And the observation here is that monads are all about sequencing. So essentially, a monad gives you the full power to change control flow. A very useful example of a monad is future. So a future says, well, I will come back later with that. And that means, of course, that I will not do this in line with the code that I'm running. I'm running this on a separate thread, and when I'm ready, then I will come back. So that's essentially very substantial changes of my control flow. And monads are great for essentially putting some structure into them. They get us out of callback hell. But monads themselves, once you have a lot of them and you need to stack them with monad transformers or whatnot, they're also very hard to deal with. So again, you should have the approach to say, use the right tool for the job. A monad is an extremely powerful thing. If I don't need it for this thing, then I shouldn't use it. And in particular, for the things we have seen, which was reading and effects, we have a very important thing, which I've shown you in the code. They're commutative. It doesn't matter what order. If I need an A and a B, I don't care in what order you pass me the A and the B, right? That's not significant. And the same thing, if I can throw an exception or write a file, and I tell you that, I'm not saying, it doesn't matter whether I say, by the way, I can raise an exception and write a file, or whether I say, by the way, I can write a file or raise an exception. It doesn't matter. It means the same thing. It's commutative. And monads, because they're so powerful, are also not commutative. So that means with monads, I cannot, in general, just swap them around. And that means the monads are much harder to compose. So the message, I think, is use the right tool for the job. Okay, we have a little bit of time. So I talked a lot about functional programming and monads and category theory and stuff like that. So I want to do something completely different and show you what implicit function types also are good for. So when we started with implicit function types, Li Hao Yi, he challenged me and says, I've seen this cool thing. I saw it in Kotlin. And it's essentially these DSLs where you can create tables. And I think Groovy has it as well. In Kotlin, it's called receiver functions, which is sort of a funky way to reinterpret this in a function type. So he says, can you do this with implicit function types? And I said, why do you think I can do this with implicit function types? And then I thought a little bit, and the answer is yes, we can. So if you have a look at it and decompose it. So what that means is you write a table, and it has 2 rows, and each row has 2 cells. And that way you build up this table. And if you know a little bit of Scala, you know that these things in the braces are parameters. And inside the parameters, it's a block with 2 statements. So this thing must underneath be mutable. So cell here and cell here, it must do something, right? And at the same time, row must do something. So that should give us a clue already. What should they do? Well, somehow the row should add itself to the enclosing table, and the cell should add itself to the enclosing row, right? So we need to know what the enclosing table and the enclosing row is. And here in this diagram, it doesn't look like we pass it as a parameter. Except, of course, if the parameter is implicit, then we can do that without actually showing it in the code. And that's precisely the implementation here. So let's maybe look at a table. So to run a table, that's the outermost one, we run the parameter of the table. That's the initialization code. That's this init. And what's the initialization code? The initialization code must know what the enclosing table is. So we make it an implicit function type. It's an implicit table to unit. We don't care about the result. So what the body of table then, it would create a new table, empty initially, run the initialization code and return the table. So what does row do? Well, row takes again an initializer, which now takes the row, the current row, and gives us back a unit, and it gets the enclosing table. So it runs the row. It creates a new row, it runs its initializer, and then finally it adds itself to the enclosing table. And finally, cell takes a string and an implicit row and adds itself to the enclosing row. So that's how I get this thing here. So very generally, why did this work? I think very generally, what implicit function types give you is the general ability to abstract over context in a type. So that means previously you had a computation and you said, well, but it needs this and this and this, and I need to be very explicit about what that is. I have to write this as parameters or whatnot. And with implicit function types, the answer is no. You can actually put this in the type of the thing you're constructing or that you're demanding, and that way we can essentially establish an implicit context. Can it be misused? Of course. So as always, the question is use these things wisely. So to conclude, simplicity is the ultimate goal. And I believe functional programming helps because it has the right genes. It gets rid of this problem of mutable state. But it's not a silver bullet. And abstraction helps, but it also has an intrinsic complexity cost. So you always need to balance the benefits with the costs. And sometimes, and most of the times, I would say, it's actually better to be plain. So I want to really make some publicity for that. Don't dare to be plain. So further reading for this, there's a paper a blog which I found extremely well written and extremely important that everybody here should read that, whether you program Scala or another language. It's called The Principle of Least Power. In short, the thing says if there are several ways to go about a program, a problem, a software construction problem, always pick the simplest possible solution that does the trick. If you can express your library as just a bunch of static methods, use static methods. Don't use a class. Don't use a factory. If you can do that with a simple class, don't use a class hierarchy. If you can do that without monads and Kleiss Lee, then do that. Use just plain parameters until it becomes unbearable that you have too many of them. And if everybody here would just do a little bit more of this attitude, then I think we would overall spare us a lot of complexities down the road. So I should finish with credits of all the people who have worked on the current Scala project and also people in the Scala Center that support Scala. And thank you all for being here. And I think we have about 4 minutes for questions.